Okay, chapter 23, Field Effect Transistors. Again, the historic significance of this is once they developed transistors, they wanted to do two things. One is increase the efficiency of the transistor. Okay, because the standard transistor, although it's pretty cool, does consume a fair amount of power. So they wanted to come up with a methodology that would increase the efficiency of the transistor. The other was to simply simplify the transistor, and thus field effect transistors were born out of that criteria. So upon successful completion of this chapter, we're going to be able to describe the difference between transistors, JFETs, and MOSFETs. Draw the schematic symbols for both P-channel and N-channel JFETs, depletion MOSFETs, and enhancement MOSFETs. Describe how a JFET, a depletion MOSFET, and an enhancement MOSFET operate. Identify the parts of a JFETs and MOSFETs. Describe the safety precautions that must be observed when handling MOSFETs. Describe the procedure for testing JFETs and MOSFETs with an ohm meter. So junction field effect transistors, JFETs, is a unipolar. Let me say that again real slow. Unipolar, meaning it has only one junction. A unipolar transistor that functions using only majority carriers. Remember majority carriers and minority carriers? Electrons and holes. It's going to be a voltage operated device constructed from either N-type or P-type semiconductor materials. Because again, we only have two materials to choose from. And this device is capable of amplifying electronic signals. Construction of a JFET begins with a substrate or base of lightly doped semiconductor material. Could either be an N-type material, N-type substrate, or P-type substrate. The PN junction is made using both the diffusion and growth methods. And as you remember, diffusion was the most popular method that we use in manufacturing. It's pretty critical that we get the shape just right. Shape is very important to get these things to behave the way we want them to behave. The channel is a U-shaped region, like if you're going to dig a channel. It's flush with the upper surface of the substrate. When made with N-type material, an N-channel JFET is formed. When made with P-type material, a P-channel JFET will be formed. I hate to do this to you, but it is what it is. No longer do we have an anode and a cathode. No longer do we have an emitter, a base, and a collector. With JFETs, we have what is called, and actually, they did this to try to simplify it. They have a source and a drain. Source and drain, that kind of makes sense, right? And to control the flow, you have a gate. So they really kind of went out of their way to try to simplify this. Yes, question?
Can the source and drain be switched off?
Yep.
Okay, so it doesn't matter.
Absolutely, yep. Can the source and drain be switched? Are they polarized? No, so you could switch them. And this is what one would look like, kind of sort of if you were an artist depiction. So this is an N channel. This is an N channel. This is made on a P-type substrate. There's our P material, and then there's our N channel. So this would be like a channel that, a channel that the English Channel, ships could pass through. Instead of ships, electrons are passing through. So this N channel is carved right out of the P-type substrate. Not carved out, typically probably diffused out or diffused in using the photolithography process. A JFET requires two external bias voltages to operate. One is going to be connected between the source and the drain, forcing the current to flow through the channel. This is going to be called our voltage drain source, VDS. Let me go back a slide so you could see this, right? Voltage drain source. That's going to be this path right here. And if you will, for lack of a better term, this is going to be like our working current. This is going to be the current that we're controlling to get her done with, to get some job done with. The other voltage is connected between the gate and the source, controlling the amount of current flowing through the channel, and this is going to be known as voltage gate source, VGS, voltage gate source. Let me go back a slide. That's going to be this voltage right here, VGS, VGS. Specifically, what that VGS is going to do is control the size of this depletion region. See, this is my P-type substrate, this is my N channel, and this right in here is a depletion region. So I can control the size of that depletion region by changing my VGS. What's up?
Is the depletion region actually visible?
With the naked eye? Yeah. No, you can't see this. It's an artist's depiction. Yeah. You can't see none of this stuff, man. I mean, I've known people that perhaps could see it. Met some people in Amsterdam that I guarantee you could probably see this. At least they'd swear to it, that they could see it. But voltage drain source is connected so that the source is made negative with respect to the drain. The current then flows because the majority carriers are electrons in N-type material. The source to drain current is going to be called the drain current. The channel serves as resistance to the supply voltage. The gate to source voltage is connected so that the gate is negative with respect to the source. The PN junction formed by the gate and channel is going to be reverse biased. This creates a depletion region around the PN junction which spreads inward along the length of the channel. Let me go back a couple slides so we could see that again, right? That's what we're talking about here. That depletion region. The depletion region is wider at the drain end because the voltage drain source adds to the voltage gate source, creating a higher reverse bias voltage. Remember how it has a kind of that teardrop? Let me go back a couple slides. That's what we're talking about, how it's wider right here. It's wider right here because this is where that voltage is sitting. So it's going to have more of an effect on this side. It's not going to be just like a half oval, if you will. It's going to be stronger influence closer to the drain. So that's why it's going to look like this, if you could see it, which you can't. So you got to believe me. You know what I'm saying? The size of the depletion region. This is really what we're talking about here. The size of the depletion region is controlled by the voltage gate source. As the voltage increases, so does the depletion region. As the voltage decreases, so does the depletion region. This is critical in the operation of these because the bigger the depletion region gets, the less current is going to flow through the channel. As the depletion region increases, the size of the channel is reduced. This reduces the amount of current flow and can be used to control drain flow. An increase in voltage gate source causes a decrease in drain current. So therefore, we could say that it's inversely proportional. In normal operation, the input voltage is applied between the gate and the source. The resulting output current is the drain current. The input voltage is used to control the output current. JFETs have an extremely high input resistance or impedance because the gate to source voltage is reverse biased. A lot of engineers like this property. High impedance could be a good thing. Is high impedance a good thing? High impedance is a good thing, right? The highest impedance device I ever saw was in Star Trek. They had that, Spock had that tricorder thing. He was able to troubleshoot sophisticated electronic equipment without even connecting it up to the circuit. That's pretty high impedance. That's no effect on the circuit. So high impedance is good because it has less of an effect on it. If you had low impedance or resistance, a lot of current would want to flow through your device. So high impedance typically is a good property. The amount of gate to source voltage required to reduce the drain current to zero is the gate to source cutoff voltage. The amount of gate to source voltage required to reduce the drain current to zero is the gate to source cutoff voltage. So as you increase that voltage, the depletion region gets bigger, 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 till it does what to current? Cuts it off. Gate to source cutoff voltage. Specified by the manufacturer. You can find that on a data sheet. The drain to source voltage has control over the depletion region within the JFET. As the voltage increases, so does the current. A point is reached where current levels off even though voltage still increases. So these first two bullet statements, you know what I'm talking about? This is like Ohm's law, right? When voltage increases, what does current do? Follows it, right? Ohm's law. Increase voltage, increase current. Well, with a JFET, what's going to happen here is the value of drain source voltage required to pinch off or limit the drain current is called the pinch-off voltage. So what happens here with these, no longer, for the low part of the range, voltage and current increase. But then what's going to happen is this. Voltage will increase, but current's going to remain because this point right here is the pinch-off voltage. Pinch-off voltage, that we increase voltage, but yet current does not increase. Again, you want to find that value, the data sheet. The main difference between P-channel and N-channel JFETs is the polarity of the bias voltages in a P-channel JFET are going to be opposite to that of an N-channel JFET. This is what the schematic diagram looks like. N-channel, the arrow's pointing in. P-channel, well, it's not pointing in. 3 leads, drain source, and you can hook those up at either way. You have no polarity associated with them. Interchangeable. And then the gate. This wasn't good enough. It wasn't good enough just to have a FET. They wanted one that would even be more efficient, more better. So what they started doing is working on developing what's known as a metal oxide semiconductor field effect transistor. That's a mouthful. Metal oxide semiconductor field effect transistor, or most commonly known as MOSFETs. MOSFETs. MOSFETs do not use a PN junction. They use a metal gate. And it's electronically isolated from the semiconductor channel by a thin layer of oxide. I want to warn you, anytime you hear this, electronically isolated, electronic or electrical isolation allows you to build up different charges on different things. That's what isolation does. And by doing so, these components are much more prone to damage. We're going to talk about that more in a bit. Damage from electrostatic discharge, ESD. There's two important types of MOSFETs. There's what's called an N-type unit that have N channels, and there's a P-type unit that have P channels. N-type units with N channels are called depletion mode devices. Depletion mode devices. That means they conduct when zero bias is applied. So basically it's like a device that is like normally on, right? It's just going to be on. And what we have to do is deplete that region to be able to start to control current. Normally it's like on full throttle. P-type units with P channels are called enhancement mode devices. Electron flow is cut off until it's aided or enhanced by a bias voltage on the gate. So this device will normally be off, if you will, until we enhance it with a voltage and begin to turn it on. This is what one of these MOSFETs would look like. Here is our substrate, P material. Here's our N channel. What we've done is put an insulating layer of material in here, and then we have a metal gate. So what will happen is the voltage that we put on the metal gate, in essence, electrostatically, will affect that N material. But the current will never flow through this insulating layer because it's an insulating layer. Now those of you that have started ELEC 115 have done some studying on electrostatic discharge, right, ESD. This is the first component that really could be damaged by ESD. And it could do so because it's electronically isolated. So what happens is you shuffle your feet across the carpet or scratch yourself or do whatever it is that you do without proper protection. You've got one electrical potential here on your substrate, and then you say touch this gate right here, and voltages as high as 30,000 volts are not uncommon for static discharge. What it's going to do is literally be like a micro miniature lightning bolt that is going to arc through the insulating layer. And I've actually seen some photographs that industry has taken in failure analysis of components, and it looks just like this, except you see like a little tiny crack in that insulating layer. What caused that crack? High voltage arc, static discharge through the insulating layer. And that's bad news, because once that occurs, components fried. Question?
If that cracks, to recycle it, then you install another layer, insulating layer?
These are all micro miniature. These are the size of a head of a pin.
Okay.
This isn't big. This is yeah, components destroyed at that point. A MOSFET is formed by implanting an N channel in a P substrate or a P channel in an N substrate, and then depositing a thin layer of silicon dioxide on the channel, attaching a thin metal layer to the insulating layer. I'm sorry? What is the metal made of? Slips my mind. Just a conductor.
Oh, okay.
Silicon dioxide is
Silicon dioxide. That's the insulator. Yep. One difference between MOSFETs and JFETs is that the gate of an N-channel depletion MOSFET can also be made positive with respect to the source. This is what the schematic symbols look like. And, ooh, look, we've added another lead. Sometimes this lead is available, so you could have a component with 4 leads coming out of it. Sometimes this lead is connected directly internal to the source. The reason that we have this additional lead, this substrate lead, is that because these devices are so efficient and they operate at such low voltages, in some cases you want to link all those substrates together to make sure they maintain that they're at a same electrical potential. So engineers will determine how those are all going to be tied together, because any difference in potential that you build up will be a voltage that can start to develop an electrostatic field, and all of a sudden you're going to have this thing doing something you don't want it to do. What's up?
Since the insulator is silicone, wouldn't it react badly to heat as well?
Absolutely. All of these can be damaged by heat.
So
Everything for the rest of this book can be damaged by heat. Everything.
that's just weird that they put a semiconductor in insulator.
Yeah, but they're doing it so, again, they electrostatically are influencing it, which means now you're not consuming as much power. MOSFETs are much more efficient. Much more efficient. If any of you are old computer old-timers playing around with PCs, inside your computer is a little battery, and if that battery dies, forgets what time it is and stuff, typically what that helps keep alive is the CMOS chips, complementary metal oxide semiconductors. They're CMOS, so they can put a little battery in that thing, and basically it will last years and years and years and years and years. Even if it's unplugged, it'll remember the date and the time. Usually not the most accurate date and time, but it will remember it. They use this technology because, again, it's highly efficient.
Yeah. But it's very heavy.
The big thing I want you to realize on the schematic symbol is generally these look like N-channel JFETs, P-channel JFETs, except the gate here is not touching. That means it's electrically isolated. So therefore you know that this is going to be a MOS, metal oxide semiconductor, field effect transistor MOSFET. Enhancement MOSFETs, a device that conducts only when a suitable voltage gate source is applied. An enhancement MOSFET does not have a conducting channel. The source and drain regions are diffused separately into the substrate. The lead arrangements are the same as with a depletion MOSFET. See, here there's no channel, and that's on a schematic diagram how they're going to make it look. So now we've got to influence this with a voltage in order to get current to flow, source to drain, and to be able to gate that. And these are even more efficient. Safe handling of MOSFETs, leads should be kept shorted together until you install them. You don't want to short them together and then turn the power on. Well, Joe said they need to be shorted together. No, shorted together when in transit. Hands used to handle the device should be grounded. You should have a wrist strap on. soldering iron should be grounded. You should be wearing a lab coat when you're handling these. Some of these devices, if you just look at them cross-eyed, they're going to blow up. Okay? They're very, very sensitive. So you've got to go out of your way to handle them efficiently, effectively. Question?
Do the wrist straps actually make a significant difference?
Huge. It's putting you at ground potential.
Oh, okay.
Wrist strap puts you at ground potential. Heel straps put your body at ground potential. And then typically you're isolated from ground by a couple million ohms. Okay, by several million ohms. But still, for that voltage, it won't build up on you. If you've ever been, there's certain stores. Where the heck was it? Oh, I was up in Fairbanks, Alaska in February for the weekend. And it was really, really, really dry up there. And anytime you moved around on the carpet, you touched the door handle, you're getting zapped. It's because the humidity was so low, it was so extremely cold and dry up there that we were very prone to generating excess of static electricity because humidity does play a factor in it. Never insert, I love this one, never insert or remove a MOSFET from its circuit when the power is on. Well, typically you really shouldn't be removing any components from a circuit when the power is on. Testing FETs, the first thing you have to determine is what type of a device is it. If a FET, is it an N-channel or a P-channel device? If it's a MOSFET, is it an enhancement or a depletion type of device? Test with an ohm meter or a commercial transistor tester, if you dare. We don't have one here because it promotes laziness. So about the only thing you're going to be able to test here is basically opens and shorts with your DMM or kicking it old school with an analog ohm meter. In summary, a JFET uses a channel for controlling a signal. 3 leads are attached to the gate, the source, and the drain. The input signal is applied between the gate and the source for controlling the JFET, having a direct impact on the size of its depletion region forming inside the channel. JFETs have an extremely high input resistance or impedance. This is a good thing. JFET schematic symbols. Up at the top is the N channel because the arrow's pointing in. The one below that, well, that's the P channel, it's pointing out. The next step of the evolutionary process of FETs is the development of the MOSFET. It's your first electrostatically sensitive component. The MOSFET is isolated. Isolate the metal gate with a thin layer of oxide. Depletion mode MOSFETs are usually N-channel and are classified as normally on. Enhancement mode MOSFETs are usually P-channel and they're normally off. In a MOSFET, the gate can be made positive or negative. Schematic symbols for depletion MOSFET. This is not the depletion MOSFET. This is the wrong illustrations. What type is this? Enhancement. Very good. You passed your first quiz. You're just not getting credit for it. The source and drain leads can be interchanged on most JFETs and MOSFETs because they're symmetrical. So your source and your drain could be interchanged. Schematic symbol for enhancement MOSFETs. These are enhancement, are they not? Yep. So we see the separately diffused regions. Electrostatic charges from fingers can damage a MOSFET. Make sure you use all ESD protocols. Technicians and equipment should be grounded when working with MOSFETs. Test JFETs and MOSFETs with a commercial transistor tester or an ohm meter. Of course, you will not have the opportunity to use the commercial tester here at Lake Washington Technical College because Peter Welty and I believe it promotes laziness. Question. Three leads. Make sure you use a 3-leaded soldering pencil These stations here are all grounded. But if you're going out just to buy one for your own personal use and it's just got 2 leads on it, then it's not grounded. So you want to make sure it's grounded.
Is it like an adapter that makes that tooling?
No, it's just the style plug that has three prongs on it. And typically, a manufacturer will not use that 3rd prong if it's not attached to anything. So if you're buying one that's only got 2 plugs on it, because a lot of home appliances have only, my electric razor has 2 plugs on it. It's not grounded because it's insulated, because it's plastic. That was the whole thing with was it Black & Decker, double insulated. Wow, that's really insulated. That means that it was grounded and it was made out of a case that was made of plastic. But then again, I remember my dad, he's got, back in Connecticut, he's got an old Craftsman electric drill, okay? And it's just a hand drill, okay? But you plug it in the wall. It's only got 2 plugs. And the case is metal, okay? So if one of the wires comes loose in there, you're basically could be holding on to 110 and then you're completing the circuit path. So we've come a long way with electrical safety over the years. So back when they used to make hand tools out of metal, I mean, that's like priceless. Dad's got a big radial arm saw, radial arm saw, cast iron arm. Takes 3 men and a small boy to move it. I mean, it just weighs a ton, cast iron. Make sense? Any other questions, comments, concerns, trials, tribulations, grief, anguish, sorrow with this chapter? All right, let's go ahead and take about a 12-minute break. We're going to kick it off again at about 6 p.m.